Okay. So is my screen visible to you? Okay. Okay. So this is the sixth class on this electromagnetic theory, and yes, in the last class I had to travel, so I could not take it on Tuesday. So this is an extra class to not extra actually, just a compensatory class for the last Tuesday's class. And if you remember, in the last few classes, we had been discussing about electrostatics and magnetostatics. We saw that static charges create electric field, then moving charges create magnetic field. So what we will be doing is basically we'll try to see what is the relation or what is the connection between electric fields and magnetic fields. See, we are studying electromagnetic theory. So now we don't study electrostatics and magnetostatics separately. We know that they are connected to each other, they are related to each other. So today's class will be based on understanding this relation between electric fields and magnetic fields and how the variations of one can lead to the creation of the other. Okay, so that is about today's class. So let us first start with electromotive force, right? So if you have any circuit, so suppose here we have a circuit, okay? And as you can see that in any circuit, we normally say that, this is the current that is flowing through the circuit. So you just switch on, if you have a switch, you switch it on and the light glows. And you say that the current flowing through the circuit is some I, okay? But the question that you know, for now, it's clear to us and we understand that the moment we switch it on, there is a uniform current flowing through it. But but if we have to imagine how we get there, right? Then there's a question that comes is that so you have some source. So why not? It's the case that when you switch on or when there is a current flowing, why can't it be the case that there are more currents flowing here while there are less currents flowing here? How can it be instantaneously equal, right? All throughout the circuit. So there, the point is that this equilibration of the current happens very fast, and that's why we know that the current actually is the same that is flowing through all of it. But now, if you consider in those transient times, if you consider that the current in some location is more than the other, such that there is some accumulation of charge, right? So there's a current flowing. So if there's more current in this place and more less in that, that means there'll be more currents coming in than moving out. So one can think of it as something like this. So you can have a kink like this where there is a net accumulation of charge. So what happens is that this accumulation of charge creates a magnet electric field which is opposite to the direction of flow of your initial current. Okay, so because you can see here, the electric field lines are pointing in this direction, outwards from the kinks, right? Because we know that electric field lines emanate from the positive charges. So that means what will happen is that then this electric field will result in movement of charges, which is in a direction opposite to the initial starting current. And this field opposes the current flowing in and promotes the current flowing out. So in a way, this balances and creates the equilibrium, right? So this is a self-correcting system in which the current gets equilibrated in a circuit. Okay. So now if we consider that what are the two forces? So one force comes from the source, that is your battery or whatever source you have in your circuit. Okay. And another force is this electrostatic force that can generate because of accumulation of charges. So now what it means is that so the net force is Fs plus E. Okay. Now we know from the definition of our potentials, we know that if you have to find what is the work done by this force. So what do? We do a line integral, right? So now if you have a closed circuit, so you do a closed line integral, right? F dot dl all over the circuit, right? Now we know that electrostatic fields, they are conservative forces. So closed integral of E dot dl goes to 0. So what remains is Fs dot dl, right? So Fs is the force that comes because of your source or your battery. Okay. So this is what is called the electromotive force. So basically, this term here is not exactly a force. It's actually work done by the source, right? Fs is the force that comes from the source. So Fs dot dl over the complete circuit is your electromotive force or EMF. And this is not actually a force. This is actually work done. Okay. So now if you consider an ideal source, which is resistance-less, so in that case, your F is actually 0. So that means you can write E as minus Fs. So that gives you a definition of your electromotive force or EMF, right? So this is your EMF. This is the definition of EMF. So EMF is given as minus E dot dl from some point A to B, or it can be written as Fs dot dl A to B, closed integral over the entire loop, where Fs is your force that comes from your source. So this is actually work done per unit charge by the source. Now, why we are talking about this is will be clear in the coming slides. But for now, we got to know the definition of EMF. Okay. Now let us talk about motional EMF. So if you remember, when I think even in our higher secondary classes, we had a brief idea about generators, right? So motional EMF is at the heart of how generators work. Okay, so let us see what motional EMF is about. So it says that this is some region, the shaded region is a region where there is a magnetic field. And you have this loop with a resistor. Okay, so this is some circuit, consider it to be some closed loop. And a part of this loop, a rectangular loop, so a part of this rectangular loop encloses a region of your magnetic field. Okay, so that means there are some magnetic field lines going across this loop, right? So in this condition, now what is told is that we pull this loop at a velocity v outwards. Okay, now as we pull this uh, loop outside, what happens? The region that is there inside the magnetic field gradually decreases. So the flux linked to this loop gradually decreases, right? So now there are two ways of looking at this event. So first we will look at it from the point of view of forces. Okay. So when you move this this wire with a velocity v, if there are some charges in this wire, what would happen? The charges will be moving with some velocity v, and there is a net magnetic field which is pointing into the page. Okay, so there is a net magnetic field. So now you have moving charges in a magnetic field. That means they should experience some force, and this force is given by q into v cross p. So if you want to find, so this is this force, right? Because they're perpendicular to each other, v cross b will be nothing but vb. So what you get is a net force that this charge experiences. The charge on this wire experiences as it is moved outside with a velocity v. So this is qvb. So the force per unit charge will be given as v into b, right? So now if you are asked that what was the work done by this force over the line integral of your loop? Okay, so what you do this line integral. So this is the work done for moving a unit charge from suppose one point of the loop back to the same point all around the loop, right? So you do this line integral, and what you get is VBH. Why H? Because now you have to be careful about direction of your force. So you have a velocity along this direction, you have a magnetic field pointing into the page, and that results in the force, the magnetic force, which is along this direction, AB, along the side AB. So BC and AD, these sides do not contribute. Why? Because the force is perpendicular to that. So if F dot dl for BC and AD will go to 0 because they are perpendicular. So only this part will contribute. And this part has the dimensions is h. So what you get is the EMF is given as BBH, right? Now let us look at it from the other point of view, which is from the point of view of what is the flux that is linked to this loop. So now what it says that for some instance, we know what is the flux, right? So if the magnetic field is B, then the flux linked through the loop is given as B dot dA, right? And a surface integral over the entire region that is inside the magnetic field. And that would be nothing but this point X into H, right? That is for some uh, point in time where the the length of the loop inside the magnetic field is X. Okay, so for the rectangular loop, pi is given as BHX. Now, as you move the loop outside, this X gradually decreases. So what happens? The flux changes, it decreases. So d phi dt is given as BH dx dt, which is nothing but minus BHV. So this shows that the flux is decreasing. So now if you relate this to, we see that EMF is given as minus d phi dt. So that means the flux change, the rate of change of flux is equal, and so the minus sign denotes the direction, and in magnitude they are equal to the work done by the source, or you can say the work done by the magnetic force. So there's a thing here. See, you write it as magnetic force, but basically this is the electric force that is generating because of the magnetic flux change. Understood, right? So there are two ways. In this definition, we write it as the work done by the magnetic force, and that's why it's VBH. But when we talk about this, it's actually the change in the magnetic flux which is resulting in this EMF, right? So the change in flux related to the EMF by this relation. So now based on this, if we try to answer this question, so a square loop of some wire uh, with side A lies on a table at a distance S, and this is a current carrying wire. It says find the flux of B through the loop, right? So in this kind of questions, first we have to see, so for flux, whenever we're asked to find flux, we need to find B and we need to find the area, right? And when we talk about change in flux, either B must change or the area enclosing the magnetic field region must change, right? So here, what happens is we know the expression of field for a current carrying wire, right? And that is a function of this perpendicular distance from the wire, that is S, right? So what we do, so we understand that the force that this part of the wire will experience, or the field that this part of the wire will experience will be different from what this part of the wire will experience, right? So because of that, we will take small segments, right? So small segments with some width ds along this. Okay. So basically what we are trying to do is the field for a long wire is known to us, mu 0 I by 2 pi s. Now we need to find flux. So we need to find the surface integral of B dot dA. And there we do an integration from S to S plus A, where the small area element is taken as A into ds. Okay. So you take small elements here and then you do an integration. So this gives you the net flux that is linked through the loop. Now the question says that if someone now pulls the loop directly away from the wire at some speed v, what EMF is generated? So now the question is that this is your flux. You are asked to find the EMF. So you can directly use this relation to see how the flux is changing, and that would give you the EMF, right? So you have to do a time derivative. So if you do a time derivative, and this minus sign talks about the direction of the flow of your direction of the induced current flow, which we'll talk about in coming slides in details. So now if you do that, you do a line integral, and it says that the speed is v. That means ds dt is equal to v. So if you do that, you get an expression. So this is how, if you are asked to find the EMF, you have to first find the flux, and then you have to find the rate of change of flux. Now, how do you understand the direction of flow of current? So one way is to see what is the direction of your force that is generated. Okay. And so from here, you'll have a magnetic field which will be pointing out of the page, and you know that there'll be a velocity, which is this this square is being taken away from the wire, right? So you have a velocity in this direction. And from there, you can use the relation to find the force. And you can see that the force will be towards right. Okay. But because the field here is different from the field here, that results in a net current, which is counterclockwise. What will be more interesting to understand is the fact that there are there are easier ways of understanding the directions of induced current from the fact that there's this minus sign here. So what this minus sign is telling us is that if there is a change in flux, then the induced EMF is such that it tries to nullify the change. So in this case, when we move this loop away from the wire, we know that the flux is decreasing because we are moving away from the source of your field. So that means you should have the induced current will be such that it will try to increase the magnetic flux, right? So here for this wires, if you see the current is flowing in this direction, so the magnetic field points out of the page. And because the flux is decreasing, your induced current should be in such a direction that the resulting field, because of the induced current, should also point out of the page, right? So now if you consider this square loop, you can understand that if you have a counterclockwise flow of current, that would result in a field out of the page. So that's why the current flows counterclockwise. Now, the next part of the question says, what if the loop is pulled to the right at speed t? So initially the loop was taken away in this direction. Now it is asked that if we take it in this direction, what would happen? So in this direction, you can understand it's actually changing along the wire, right? While the magnetic field is not a function of, it does not depend on where you stand along this line. It depends on the perpendicular distance, right? So if you move the loop along this line, the magnetic flux that is linked do not change. So in this case, there will be no change in flux. So the EMF generated will go to zero. Okay. So based on how the flux is changing, one has to find the EMF. Okay. Now this concept of EMF or the motional EMF led to some interesting series of experiments. Okay. So in 1831, Faraday reported this series of experiments which tell us a very important point. And this lies at the start of how electric and magnetic fields got connected to each other. Okay. So the first point is that this is something which we just discussed. So you have a magnetic field and you have some loop with a current flowing through it. And then you pull it in this direction with some velocity v, and sorry, see, when you move it in this direction, there'll be an induced current, right? And because of that, you get a net EMF generated. Now, what this is another experiment which says that now you keep the loop constant, and what you do, like in a fixed position, and you move the magnetic field region in the opposite direction. So basically, you're doing the same thing, but now your loop does not move. It's the magnetic field region which moves. So basically, suppose you can imagine you're taking the magnet away. Okay. So what was seen is that this resulted in the same induced current. Okay. So you also got to see an induced current in this case. Okay. And this was even more interesting, which said that here we did not move anything. So here neither the loop was moved nor the magnetic field region was moved, but yet there was a induced EMF that was generated. Why? Because there was a changing magnetic field. So only the magnetic field in this region was changing, but there was no motion involved. Okay. So that led to this idea that actually what is causing the change is not the motion. It's not the motion of the wire, or not the motion of your magnetic field region, but basically the change in flux. Okay. But this caused a confusion. Why? Because we know that magnetic forces can only exert magnetic fields can only exert force on moving charges. So now if nothing is moving, how come there is a force that is generated, right? So nothing is moving, everything is at rest, but yet there is a force that is generated. So how do we understand that? So that led to this idea that maybe because of this changing magnetic flux, there is an electric field that is generated. Okay. So this led to the concept that a changing magnetic field can induce an electric field. And it is this electric field which is resulting in this force and the induced current. Okay. So now if we think about it mathematically, we know that EMF is given as closed integral E dot dl is equal to minus d pi dt. Okay. And we know what is phi. Phi is your flux. So it's nothing but integration of B dot ds or dA. So now if you use the Stokes relation and try to write this integral, the line integral in terms of the surface integral, you'd get this relation, which says that curl of E is equal to minus del B del T. So initially, if you remember in the case of electrostatics, this was zero. Curl of E was zero. And that will also be the case here, because if everything is static, then there's a constant B. So this term goes to zero. But what this is telling you is that now when you have a changing magnetic field, this changing magnetic field results in an electric field where the curl of E is given as minus of rate of change of magnetic field. Okay. So this is how the Faraday's law got. So later we'll see that when we talk about Maxwell's relations, this is how it got modified. So in the electrostatic case, we have it as zero. Later we have this minus del B del T term. Okay. Okay. Now, based on what we had discussed till now, this is a question which says that you have a conductor of a given length. It moves at right angle to a uniform field flux density with a given the magnetic field intensity is given, and you have a velocity of 50 meter per second. So what is the induced EMF in the conductor? So this is a pretty standard straightforward question where you have to use your concepts of motional EMF we just discussed, right? So basically what we have to do is the answer would be 75. Let's see how we get there. Okay. So first is this is the same question that we discussed. So this is a magnetic field, and you can see that the magnetic field line is perpendicular to the direction of your direction of motion of your conductor. And as you move the conductor with some velocity v, okay, and the length of this region is given as L, which is 100 centimeter. Now, as you move, what happens? We again get back to this. So the rate of change of flux is given as minus ddt of BLX. So that is equal to BLV. And we know what is V, we know what is L, and we know what is B. So if you put those values, we'll get an expression of the induced EMF. It's important to note that here L is actually the L which is along the magnetic force. Okay. So this dimension does play a role. More is this dimension, more will be the EMF. Okay. So now if the conductor length moves in a magnet, so here it was perpendicular, but that might not always be the case. So if there is an angle between the length, okay, this L, and the direction of your motion, that is the velocity. So if the velocity makes an angle with the magnetic field, okay, so in that case you have to remember that the force goes as V cross B, right? So because of that, you will have this sine theta component which will come in the electron EMF expression. EMF is nothing but work done by the force, right? And force we have this relation between V, that is velocity, and magnetic field, which is given as Q into V cross B. Because of that, you have this sine theta component. So if there is an angle between the magnetic field and the velocity, this is how the EMF will look like. Okay. So now let us talk about that minus sign that we were discussing. So as we saw that the minus sign tells us that the EMF is in such a direction that the induced current flows such that the change that produces this current is nullified. So nature abhors a change in flux. Okay. And this becomes useful in understanding the direction of your induced currents. Okay. So now let us try to solve some questions based on this rate of change of fluxes and try to find EMF in different conditions. Okay. And these are pretty standard questions which can come in different exams or assignments. So here it says that you have a square loop with some site A, which lies in the first quadrant. So now it says that you have a non-uniform time-dependent magnetic field. Find the EMF. So whenever you have to find the EMF, that means there has to be, so if the EMF is non-zero, that means the flux is changing. For magnetic flux to change, either the magnetic field has to change or the area has to change, right? Because these are the two terms that is involved in the flux definition. So here what it says is that the area remains constant, but it's the magnetic field which is time dependent. So the magnetic field is changing, right? So what you have to do, you have to find EMF. That means you have to find rate of change of flux. So first let us find flux. So flux is given as B into dx dy. That is the surface integral of B, right? And here's because you have this y cube term here, so you do an integration over x and y separately because your magnetic field is a function of y as well. So you do this integration and this gives you the net flux. And as you can see, this is a function of time. So now what you do, you have to find EMF. So you have to do d phi dt. So minus of d phi dt will give you EMF, which is again a function of time, as you can see here. Okay. So this is one kind of question. Another could be something like this. So here you have a long solenoid with some radius A, which is driven by an alternating current, so that B is again a function of time. Okay. And you have a circular loop of wire of radius is given and the resistance is specified as R. It is said what is the current that is induced, right? So what do we do? So we know that B is changing. That means the flux will change. Okay. The area is still constant. So we have to find the flux. The flux is given as area into B and B is time dependent. So that means we can find EMF, which is minus d phi dt. So this is your expression of EMF. Okay. Now, because the resistance is known to you, what you can do, you can use this relation, use the Ohm's law to now find the current. Okay, so current is given as V by R. So this is how the current looks like. So similar kinds of questions was, I saw a similar question in the last year assignment, which was something like this. So here it says that if you have a conducting circular loop of some radius. So the radius again is given here. Okay. And you see that the magnetic field is a function of time. So it's changing with time. Okay. So now what is the induced voltage in the loop? So based on what we had just discussed, can you try to find the answer? So here, as you can understand, we have to find induced voltage. That means we have to find EMF. And for EMF to be non-zero, the flux should change. Here, as you can see, the area is not changing. So what is changing is actually the magnetic field, right? So now using this relation, this same procedure as these questions were done, can you try to tell me what the answer should be? Try to see the chat if you can write in the chat if you have an answer. So here, like if we compare with this question, see, we know what is R, right? So we know what the area is. Area is pi R square. And we know that B is again a function of time. So now if you do d phi dt, you would get a similar expression. You would get something like pi R square B naught omega sine omega t, where omega is given as 377. And remember, you have this milliweber term here. Okay, so be careful about the units. So it's 10 to the power minus 3 that you have here. Okay, and if you use that, you'll be able to find the expression for the voltage. So basically the same procedure. Okay. Okay. So now that we know that in case of the cases where you have a changing magnetic field, the change in magnetic field results in a non-zero curl in E. Okay. So now using Faraday's law, you can write curl of E equal to minus del B del T. And from Ampere's law that we had discussed before, we know that curl of B is equal to mu naught J. And if you now consider a region where there is no free charge, that means rho is equal to 0. That means Gauss's law becomes divergence of E going to 0. And again, this is always true, right? Divergence of B is always 0. So now if you just look at these four expressions, you can see that there is a similarity between the electric field and the magnetic field. So you find a parallel, right? So Faraday-induced electric fields, which is given by this expression here, are determined by minus del B del T, that is change in magnetic field. In the same way as magnetostatic fields are determined by mu naught J. So this is the parallel that you get. Okay, and you can try to write the same expressions in terms of integrals, which will be given as closed integral of B dot dl is equal to mu 0 I, and again closed integral of E dot dl, this is from here, right, is equal to minus d phi dt, right? So these are the integral forms and this is the differential form. So now based on this, it says that a uniform magnetic field is pointing straight up, okay? The shaded region here, as you can see, this has your magnetic field. And now it says that if B is changing with time, what is the induced electric field? Okay. So how to answer this question? So you can see that the magnetic field lines is pointing upwards, right? Now, if B is changing with time, that means again the flux is changing. So the induced EMF or the induced electric field will be in such a direction that it will try to nullify that change, right? So what you can consider is you can consider a small Amperian loop. So basically we are now using this parallel that we just discussed. So if you use this relation, so we take a small Amperian loop of some radius s inside this region and we do a line integral. So what do we get? E into 2 pi s is equal to minus d phi dt. And what is phi? Phi is nothing but area, that is pi s square into b, right? So that means now you know how the EMF is dependent on the rate of change of magnetic field, right? So that means if B is increasing, E will run clockwise, and if B is decreasing, it will run counterclockwise. So based on how the flux is changing, this is the relation which will tell you how the induced EMF is dependent on the change in magnetic field. Okay. Now, this question is a pretty fun question. And here it says that you have a line charge. Okay, so in this big ring that you have, along the ring, along the circumference, you have a line charge lambda. Okay, and the radius is given as b. In a smaller radius here, which is a shaded region, there is a net magnetic field which is pointing up. Okay, and it says that now someone turns the field off. So now what happens? Right? So obviously, once the entire field goes to 0, that means there'll be no flux, and later so there'll be no EMF. But during this change from B naught to 0, there's a transient time, right? And at that time, the flux is decreasing. So that would result in a net EMF, right? So we have to find that. So we have to see how that induced EMF, or what does that induced EMF do on this line charge, right? So here we know that the magnetic flux was initially pointing up and now you switch it off. So when you switch it off, that means the flux is decreasing. So that means the induced current will be in such a direction that it will try to nullify the change. So that means the induced current will be in such a direction that it will create a magnetic field, which will again be pointing upwards, right? So that will tell you that you will have a rotation which will result in a net. So there'll be a net electric field in this direction, which will try to cause a, a net magnetic field in the direction upwards, which will try to nullify the initial change that was created by turning the field off. Right. So this is how induced EMF can, be very you can say active in this kind of questions. What's important to note is that it is not the magnetic field that is doing the work here. It is actually the electric field. Okay. It's important that in this region, there was no magnetic field, right? Magnetic field is only in the shaded region. But yet you get this rotation is because of the electric field, which results from the change in the flux. Okay. It's important to note that, there was no magnetic field in this region. You switched off the magnetic field in this shaded region, but that resulted in an electric field automatically, and it was the electric field which turned the wheel. Okay. Okay. So now that means before Maxwell, this was our relations, right? This is what we had discussed. This is the Faraday's law. Okay. And now we will see that there'll be an additional change to this Maxwell's relations, which will come up. Okay. So why is it so? So there's something wrong with the Ampere's law, and let's see why. So the first point is, if you take this expression and if you do divergence of curl of E, we know that divergence of curl of E goes to 0. And this is consistent, right? Because divergence of B is always 0. So that means this holds. So nothing wrong with the Faraday's law. But now if you do the same for the Ampere's law expression, what you see is that you get this mu naught J term, right? And mu naught J is not necessarily always 0. It is 0 only in magnetostatics, right? It is 0 in cases of steady currents. It's not 0 otherwise. So that means this there's something wrong. This does not hold always, right? And this was the change. So something has to be changed here, and that change was brought by Maxwell. Okay, and let's see what was done. So what he did is that we know from continuity equation that divergence of J is given as minus del rho del T. And from the first law that we just wrote here, we can write rho as epsilon naught divergence of E, right? So if you do that substitution, you get this expression of minus divergence of epsilon naught del E del T. So that means now if you combine this term with J, this effective term that you have will always be divergenceless. So that is what was done. So he added this extra term of mu naught epsilon naught del E del T to the Ampere's law. Okay. And what this is now telling you is that suppose if you consider a case where, where there is no J. Okay. So consider a case where there is no steady current, but you have a changing electric field. So that means this changing electric field can result in a magnetic field. So a changing electric field induces a magnetic field. Similarly, in Faraday's law, we saw a changing magnetic field induces an electric field. So this shows how intertwined electric and magnetic fields are. So this was how this connection was established, and that's why we are reading electromagnetic theory together today, right? This term here, epsilon naught del E del T, is termed as the displacement current. Okay, so that now there could be questions based on questions to find displacement currents. So there you have to use this relation, and you have to remember that in questions you might not directly get the value of electric field. Suppose there can be questions where the potential is given. So then you have to use the relation between potential and electric field in order to find the displacement current. So we know that E is given as V by D, right? If there is some distance over which you have the electric field and you see that the potential in this region is V, then E is given as V by D, right? So you might have to use those relations to find the displacement current. So this was one such question which came in last year's assignment, which said that you have a 50-volt generator at 10 megahertz connected to plates of air dielectric parallel plate capacitors. The plate area is given, the separation distance is given. You have to find the displacement current, the maximum value of displacement current. Okay. So how do you do this? So here the first point that you have to do is here the electric field is not directly specified, right? So you have to find the electric field from the potential. You know the potential difference between the plates and you know the distance between the plates, right? So that means E is given as V, that is 50, by D, that is 0.1 mm. So that gives you V, right? But now this is changing. right? So this is just the magnitude that we just discussed. It is at 10 megahertz. So that means the potential is actually a sinusoidal potential. It's something like V naught sine 10 megahertz t, right? V naught sine 10 into 10 to the power 6 into some 2 pi. So basically, this is in hertz. You have to remember that this is in hertz. When you write omega, it's in radians per second. So you have to multiply by 2 pi, right? So basically, what this is telling you is that your potential has an expression of 50 into sine 2 pi 10 into 10 to the power 6 t, right? So that is your potential. And you know that electric field is related as V by D. Again, D is known. So now if you use that relation, you know that del E del T is nothing but 1 by D into del V del T. And what is del V del T? Del V del T will be, so you have a sinusoidal function, so you know how to do the derivative, right? So that will give you the expression of your JD. Now the question asks the displacement current, right? In milliampere, you have to understand that here you have this area involved. So when you first do it, in terms of current per unit area. So now when you have to find the net displacement current, you have to finally multiply by the area. So that will give you the displacement current in amperes, right? The net displacement current. So that is how you have to answer this kind of questions. If electric field is not directly given, try to find it from the potentials. Okay, so now if you look at Maxwell's relations, this is how the Maxwell's relations now look like. Okay, so this comes from the Faraday's law and this comes from the Ampere's law with Maxwell's correction, which is because of this displacement current term. Okay, now let us move on to electromagnetic waves in vacuum. So what are waves? Basically, wave is some function of position and time, right? And it follows this relation which says that basically the, so if it is in 1D, you can write it as del square f del z square is 1 by v square del square f del t square, where v is your velocity of the wave. Okay. And basically, this is the Helmholtz relation or the wave equation, which a wave satisfies. And here, if you consider any wave, especially if you consider some periodic waves, so there you would see that there'll be this kind of periodicity in position and periodicity in time, which would specify the kind of wave that you have. So if you have a sinusoidal wave, suppose this is how a sinusoidal wave will look like. So this is a cos kz minus omega t plus delta. So here this k term here, the kz denotes the direction of your wave. So this is propagating in positive z direction. And the omega is actually the frequency. So the time period will be given as 2 pi by omega. The lambda will be given as 2 pi by k. Okay. So this is how you define a wave. Now, let us now go back to the Maxwell's relations. And what we see here is that if you consider regions where there is no charge and no current, that means where rho is 0 and J is 0, in those regions, your Maxwell's equations boil down to these four equations, right? And now if you use this expression, this relations of curl of E and try to use the identities, you would get this expression. It's important to note that here you have put divergence of E to be 0 because rho is 0. There is no additional, free charge or free current. Okay, so that means from here you get curl of E is equal to minus mu naught epsilon naught del square E del T square. Okay, and you can see that putting divergence of E going to 0, what you get is this relation here. Similarly, you can do the same thing for B. And again, here you will get a similar relation. So now if you compare this to the first wave equation that we were discussing, so this is in 1D, right? Because it's in 1D, you have del square f del z square. If it is in 3 dimension, you would have a del square term here, right? So that means these are, so if you compare this shows that now v, that is the velocity, the wave velocity, in this case can be related to 1 by mu naught epsilon naught. And that is nothing but the speed of light. So this proved that light is an electromagnetic wave which moves with the speed of light. Okay. So this is the wave equation. Okay. So now, since in this case, your divergence of E and divergence of B goes to 0, so we can now use our boundary conditions and we can see that the Z components, that means the normal components, so not normal, it's the component along the direction. So here we started with the wave along the Z direction. So the wave is moving along the Z direction. So that means if you use this relation, you see that the components in the propagating direction goes to 0. So this shows that the electromagnetic waves are transverse. And now if you use this expression, the expression that we found here, okay, this curl of E equal to minus del B del T, you can use it to find E when B is given or vice versa. Okay. So from here you can write, so consider that you have this K dot R minus omega T kind of dependence. Okay. So that means when you do curl of E, you will have this kind of components where K will come up. While here, when you do a time derivative, your omega will come up, like because your frequency, you have omega T dependence. So omega comes up. So that means in a more compact way, you can write it in this fashion. So that means Kz gives you the propagation direction. E is your electric field. Okay. And this is the relation which electric field satisfied with magnetic field. And they are in phase and mutually perpendicular. Okay. So that means in questions, if electric field is given, you can use this relation to find the magnetic field. Okay. Now, what is the energy per unit volume stored in the electromagnetic fields? So in case of electrostatics, we saw that the energy is given as half epsilon naught E square. Similarly, for magnetostatics, we have V square by 2 mu naught. And now because you have electromagnetic waves, so you have contributions from both electric and magnetic fields. And what's interesting to note that the electric and magnetic field contributions are actually equal. Okay. So this is how the energy will travel. Okay. And if you want to find the energy flux density that is given by the Poynting vector, so it's important that when you do E cross B, what do you get? You get the direction along the propagation direction. So that means your energy flux density is propagating along the direction of your wave. As the wave is propagating, it is taking the energy with it. So that energy flux is given by the Poynting vector, which is given as E cross B by mu naught. So these relations are very useful, and there can be very standard questions just by using these relations. But it's important to know this definitions because they have huge implications. So when we talk about you know suppose when we have two waves, okay, so you have even in thin films, when we talk about how much of the, suppose you have lights and you have thin films and you say how much of the light is reflected, how much of the light is absorbed, and all those kind of questions is actually this kind of Poynting vectors and this values that becomes useful. Okay. Now, this is one question. So these are now standard questions based on what we just discussed. Okay. So consider a solenoid with a radius r and n turns per unit length. It has a time dependent current. So the current is changing. Now, the magnitude of electric field at a perpendicular distance r less than capital R, that is somewhere inside the solenoid, okay, from the axis of axis of symmetry of the solenoid is how much? So that means you have a solenoid, you have a magnetic field. So whenever, if you have a constant current flowing through a solenoid, you know that the magnetic field is given as mu naught Ni, right? We discussed it in magnetostatics. But now this current is changing with time. Now, because it's changing with time, that means the flux that is linked inside the solenoid, that is changing. So that would result in a net electric field, and we have to find that. So that means you can again use this relation. So this is again this same relation, right? This is the relation that we will be, let me just go back. So this is the relation that we are again using, which relates flux, that is change in magnetic field fluxes, with electric fields. Okay, so that is the relation that we are using. So here we use again closed integral of E dot dl is minus dB dt dot dA, right? Because in flux is actually the magnetic field that is changing. So we know magnetic field is changing because current is changing. So you can write it as mu naught n di dt, right? And you can do this integral. So this gives you, this is just calculation. So this gives you the value of your electric field. So this is how a changing current in a solenoid can result in a net electric field inside. Okay. In this question, what it says is that the electric field is given. Electric field of an electromagnetic wave is given. Okay. You have to find the associated magnetic field. So what is the relation that you have to use? So if we go back, we have to use this relation, right? So this relates for an electromagnetic wave in vacuum. This is what is the relation which relates electric field to magnetic field. Now in our question, our electric field is given. We need to find B, right? So for this, we also need to find what is K, right? What is the wave vector and what is omega. Now this information is already hidden in E. How do we find that? So here, if you see, your electric field has a form of E naught cos some x, y terms minus some time dependent terms. That means now if you compare it with E naught cos k dot r minus omega t, then what do you get? 1000 pi will be equal to omega, right? And this term here, 0.3x pi plus 0.4 pi y, this term is nothing but k dot r, right? So now if you compare, that means this is your k vector and this is your omega. Okay. So now you can directly use this relation in order to find your magnetic field. Okay. And this is how the magnetic field will look like. Okay. So the answer in this case will be B. So there can be similar kinds of questions where you know the electric field, you have to find the magnetic field, or vice versa. Okay. And later you'll see how this expressions change when you have dielectrics. Okay, so there we have to consider the dielectric constants, and those terms will be important, and that we'll discuss in the coming classes. Now this is another question which says that there is a current IP flowing through a primary coil of a transformer, and this is how the current looks like. Okay, the question says what is the current through a secondary coil. So now if we just recall what is a transformer. Basically in a transformer you have a primary coil and there are some number of turns. There's a current flowing through it. That means it will result in some magnetic field. Now this magnetic field lines are linked to a secondary coil. Now if you have a alternating current in the primary coil, that means you have a time varying magnetic flux. So the flux that is linked to the secondary coil changes, keeps changing. Now, because there is a change in flux that is linked to the secondary coil, that results in a net induced current in the secondary coil. Right? So that is how the transformer works. That's the basics. So now what it says is that this is how the primary coil current looks like. You have to find how the current in the secondary coil looks like. Right? So here you have to remember what results in the current in the secondary coil? It's the change in flux that is linked from the primary coil to the secondary coil. Now, what is causing the change in flux? It is the change in the current in the primary coil. So that means the current in the secondary coil is actually linked to the change in current in the primary coil. Okay. So that means IS is the current in the secondary coil is proportional to minus dip dt. Okay. Minus again comes because of the Lenz's law. So now if you use that, you can just compare this to all these four options, and you understand that the current in the secondary coil is proportional to the slope of this curve, right? So here you will have a constant slope. Here the slope will go to 0, and here again you have the same slope but in the opposite sign. So this matches with this answer. So this is how you know this electromagnetic induction finds application in transformers, which is widely used, right? Okay. Now this is another question which says that here you have a magnetic field in the x greater than 0 region, and all other region it goes to 0, and you have a rectangular loop in the xy plane. with the side specified. So you have side L in the x direction and H along the y direction. Now it says that you move this from x less than 0 to x greater than 0 at a constant velocity Vx cap. So the velocity is along x direction. Now, which of the following values of L and H will generate the largest EMF? So here what you have to understand is this is how it looks like. So you have field here. There is no field anywhere else. The velocity is along x, and this is how the dimensions are. So the dimension along x is L, dimension along y is H, right? So here you have to understand that when will the EMF be largest? So let us remember the definition of EMF. In EMF, it's nothing but some work done, right? So it's force dot dl. So that means the EMF will be largest when your L, the length elements that is parallel to the force will be largest. Understood? So if you have some force and you know the direction of the force, when will F dot dl be maximum? When the dl that is along the force, when that term is maximum, then F dot dl becomes maximum, right? So that means you have to try to understand what will be the direction of the force, right? And the dimension along that direction of the force. If that is maximized, then the EMF will be maximized. Okay. So here you know that the magnetic field is pointing upwards. The velocity is along x. Okay. So can you tell me what the direction of the force will be like? So in what direction will the force be? The force will be perpendicular to both velocity as well as the magnetic field line, right? So that means the force should be along y, right? Yeah. So now if the force is along y, when will EMF be maximized? When the dimension along y is maximum, right? So now if you use that concept, can you tell me what the answer should be? Dimension along x is given as L, dimension along h is given as y. So that means if the force is along y, that means when h is maximum, your EMF will be maximum, right? That means the answer should be B, right? So this is how flux is linked. Flux is linked as B into H into X. Okay, so H is the dimension along Y, and that means your EMF is proportional to H. So the answer should be B. So this is the same thing that when we had discussed about motional EMF, you would see that it is the dimension which is along the force. It is not the dimension along the direction of velocity. In most of the cases, we do this mistake. We consider the dimension along the direction of velocity. But it's actually the dimension along the direction of force, which contributes in the EMF. Okay. So in this case, the answer will be B. Okay. Now this is another question which says that you have a conducting circular loop with the area is given. Okay. And the magnetic field is changing with time. This is how it's changing. So we have to find the charge flowing through any cross section during the time t equal to 0 to t equal to 40 milliseconds. So this is the first point. Okay. So charge flowing, that means we have to, there'll be a net, the magnetic field is a function of time. So there'll be a net EMF. There's a net EMF, there's a net induced current, and current is nothing but flowing of charges, right? So you have to find the net charge that flows in 40 milliseconds. And then the loop resistance is given. We have to find the thermal energy. So how do we do it? So the area of the loop is given, magnetic field is given. Okay, magnitude is given as 0.2 Tesla. Omega is also given, which is the frequency of change of magnetic field, and the resistance is provided. So that means the flux through the loop at any particular time would be given as P into A B is equal to B naught sine omega t into A. Now, because you have this time dependence, you have a EMF, which is given as minus d pi dt. And this is how it looks like. So now if you want to find the current, this is EMF. So current is nothing but V by R or E by R. And this is the expression of your current. So now this is the expression of current. You have to find the charge flowing. So here what we see is that if you try to find what is the time period. So if you try to find the time period of your current, you would see 2 pi by omega. Now what is omega? Omega is 50 pi. If you put that, you get 40 milliseconds. So basically you have to find how much charge flows in a time period. So now this is your expression of your time period of your current. So you do an integration from 0 to t, capital T, right? So if you do that, the net charge comes out to be 0, which is true because you are considering a complete cycle. And now when we talk about thermal energy means you have to remember the ohmic losses, right? We know about the fact that if there's a current I flowing through a wire, and if R is the resistance, then the heat generated is nothing but I square R, right? So here you have to find the energy. So you have to do I square R into dt. So that is power. This is energy. So 0 to t. And again, t is your actually time period. So you do an integration. This is normal integration that one has to do using the trigonometric relations. And this is how you get a value. So this is how you can see that, you have to use normal, our understanding of electromagnetic induction. At the same time, you have to remember our basic understanding of ohmic conductors and ohmic circuits, and use those relations in this kind of questions. Okay, so I think that is it. Do you have any question? Okay, so if not, then thank you. You can go through the questions, and later if you also have a question, you can ask me. Tomorrow we'll also have another class as usual. This was for the last Tuesday. Okay, see you tomorrow then. Thank you. I'll stop the recording. If you have any doubts, just get back to me tomorrow. Okay. Thank you.